Okay, I'm going to go through the next part of this run through. So this is for the June 23 exam for the Pearson Edexcel International Physics Unit 5. Okay, so this was the first year where the grade boundaries were suddenly increased in the international A level. I think quite unfairly, because this exam wasn't really testing Unit 5 until 2020. So this exam, the first time you could sit it was probably in 2020. And that was when it was affected by COVID. And then suddenly, so all the grade boundaries were low. And suddenly in June 2023, they increased the grade boundaries like substantially, especially for Unit 4 and 5. And students who'd been preparing on the available exams previous to that, which would have been up to January of 2023, the grade boundaries were very low. So what happened was suddenly they increased them, and students who were getting high marks, high grades in the papers which were available on the Pearson website until then, were then shocked to see that their grades were not in line with the grade boundaries from January 23 and before that. Whereas the linear exam warned people, and also all their exams came in the summer of 2023 for linear, they were told in advance the modular. So if the student had taken, say, Unit 4 in January 23, he would have got a much higher grade than if he'd taken it in June 23. That's as simple as that. And we're talking about like 20-30% increase in grade boundaries suddenly. So you shouldn't use grade boundaries from June 2020, from whenever 2020, the first exam, till January 23, the grade boundaries are not reliable. Okay. Now in this topic, in this run through, so I've done part 1 was multiple choice, and I actually did question 11, which was on radioactivity, beta decay. And in this run through, I'm going to go through what they call radiation, which really we're talking about atomic and nuclear physics. So I don't know why they put radiation. The reason they put radiation, I think, is because there's also like atomic spectra, which produces photons, E equals HF, and they just wanted to put one word because in the spectra we use them to analyze cosmology. We use them to analyze recession of distant galaxies, how they're moving away from us. But in today's run through, I'm really focusing on the nuclear questions. Okay, so we're going to go through question 11 very briefly again, question 13, question 16 and question 17 today. Okay, so if you found the previous videos useful, don't forget to give me a like, share it, write a comment. A positive comment always is nice to see, and make sure you subscribe so you know when future videos are uploaded. If you're doing linear, make sure you use these modular exams, because there's 3 per year, to prepare for doing your linear mocks. Okay, that's the best way to do it. Okay, so the first question we did was after the multiple choice. I showed you this question, question 11. You can see it's got beta decay, nuclear balanced equation. Okay, so we've already done beta decay, and you had to explain how you're going to convert electron volts, or joules into electron volts, or vice versa. Okay, so they're giving you 2.6 kilo electron volts, and you've got to change that into joules by multiplying by 1.6 times 10 to the minus 19, so you can work out the velocity of the particles. In this case, it was an electron. So if you remember how to do that, that's great. If not, you can go back to part 1 and watch the video where I explain it more in more detail. And question 11, it came before the mark scheme. That's why I did it, because it was the way I put together the mark scheme. So here is question 11. if you want to have a quick look at it. Before I go into question 13, you can stop the video. Okay, so we've done beta decay. We know how to change electron volts into joules, yes, and you know how to then work out kinetic energy of particles, okay? Remember that over here they've made an assumption, which is not necessarily always true. So question 13 is the next one we want to go to. So question 12 I did in the part 2 of the video. Question 12, I put all of the thermodynamics questions, anything to do with gas laws, kinetic energy, change of state, I put in another video on thermodynamics. So it's question 12, 14 and 18 are bunched together. So here's question 13. You'll see that now, again, we're talking about beta particles and alpha particles and tracks of. So here's a cloud chamber, which some schools may have, and you've got like a source of radioactivity at the base, and inside you've got a vapor, and these particles, alpha and beta particles, they can ionize the air as they pass through the cloud chamber. Okay, it's called a cloud chamber because it makes vapor trails. And usually in a school one, they use some kind of alcohol, which is volatile. So liquid droplets, alcohol liquid droplets, form around the ions. So if the ions are going straight, you will see the path that they've taken because the droplets form visible tracks, as shown. So this is a very simple form of a detector. And remember in Unit 4, you did particle physics where they used detectors to understand the tracks that are being made, whether they're curved or straight. Okay? So the student looked at the tracks and made the following observations. So this is the view, obviously, from above. Okay? The alpha particles' tracks are thick and straight. Yes, because alpha is, the key words you need to remember in your exam is highly ionizing. So alpha particles are large, charged particles, same as a helium nucleus. Whereas the beta particle tracks are thin and twisted. Okay? So they want you to understand and explain why these differences occur. Okay? So if alpha particles are highly ionizing, beta particles are not as highly ionizing. So this is a 4-mark question. So it's qualitative written answers. Alpha is more strongly ionizing than beta. Okay? So that's the difference. So the alpha tracks would be thicker than beta tracks. If they're more ionizing, they're going to attract more of the vapor particles, yes, to them. So that's one linkage, yeah? Then alpha particles are about 8,000 times more massive than beta particles. If you think about it, alpha particles are made of 4 protons and 4 neutrons, and a beta particle is made of 1 electron. So they will not change direction as easily, yes, due to the conservation of momentum. Okay, so that's another difference. So they're not going to be thin, they're not going to be twisted so easily, they're not going to be able to change direction so easily, they're going to be straight. Okay, so the first bit was looking at the thickness versus thinness, and the second tick, let's do this one in red, the second tick is talking about why one is straight and one is twisted, because they will not change direction as easily because they're 8,000 times more massive. Okay, go back to green. So straighter tracks are alpha due to their greater mass. So you're making the linkage between what you observe and the reason behind it. Explain. Thicker tracks are due to the greater ionizing ability of the alpha. So they attract more water particles because they've ionized more of the gases inside the Wilson cloud chamber. So this is actually called a Wilson cloud chamber in schools. Okay, hope that makes sense. So they basically wanted you to explain those observations between thick and thin, straight and twisted, highly ionizing, keywords, and mass or momentum. Yeah, more massive or more momentum would possibly get you the marks. So that's your 4 marks. So question 13 is not too difficult. Question 16 we're looking for next. Let's see if this is question 16. That's question 15. Question 15 I'll do in a future video. Looks like it's on oscillations. So we'll do a run through on oscillations. So here you see we got alpha particles again. Yeah. So it's a theme that we're going through, and also then these videos can be used to revise just that topic if you want to just do like topic revision. So it's a bit like Save My Exams except on YouTube. So I'm making topic videos from now on. I think that would be a nice theme to try and include when I have time to do shorter videos. Okay, don't forget, if you find them useful or if you have any requests, you can become a member now. And if you have requests and you're a member, I'm more likely to pay attention to them, because you will pay a very, very small fee, and that allows you to come to the head of the queue, because I've now over 1,300 subscribers, so I will not be able to get around to everyone's queries. A nucleus of thorium-234 is unstable and decays. So now we're talking about radioactivity before we talk about ionization. It decays into what? A nucleus of radium-226. How? By emitting an alpha particle. So it's alpha decay. Yes. The table shows the masses of the particles involved. So before we had thorium, after we got a split of the mass. Okay? Now if you add these two masses up, you'll probably notice that they're not exactly the same as the mass before. Yes? And the difference is you will have a mass defect, yeah, which you can then use in Einstein's equation of E equals mc squared to work out the energy released in the process. Now obviously alpha decay is a way of a nucleus becoming more stable, okay? It will increase its binding energy per nucleon, and binding energy is what binds the nucleus together. Determine the energy in joules released, yes, so that means this equation, when a nucleus of thorium emits an alpha particle. Okay, so I've already explained the concept to you. You want to work out the mass defect. So the change in mass will be the mass of the thorium minus the addition of the masses of the two particles which we end up with. So you add those together, you'll notice that you have a difference of 5.1 times 10 to the minus 3 mass units, which they've given you what it is in the data sheet. Okay, in the data sheet you'll be able to see that one mass unit is 1.66 times 10 to the minus 27 kilograms, okay, to 3 significant figures. So once we know the delta M, we can then use, so we need to change the delta M to kilograms. And once you got it in kilograms, again 3 significant figures is sufficient. You'll be able to use E equals mc squared, where M is the mass defect, and you just multiply it by c squared, 3 times 10 to the 8, and you'll get the energy in joules. So basically it's a conversion of energy units. And remember, mass is a form of energy, okay? It's like a condensed form of energy, okay? You could say that mass is light slowed down and condensed. If you can imagine condensing light into something which isn't moving, when light moves at the speed of light, yes, or electromagnetic waves are going at the speed of light, they're liberated from the constraints of being a mass, whereas when you're a mass, you have a rest mass, and you've changed to, basically it's like frozen light, condensed light. I like that concept, okay? Determine the time taken. Now it wants you to determine the time taken in years for 90% of the thorium to decay, right? That means the final value of N will be 0.1 of N naught, because they want you to use this equation, that the number decreases, and you could put N and N naught in the same side of the equation as a fraction, and we know the fraction is 0.1 because that's 10%. So if 90% has decayed, 10% is remaining, so the fraction 10% is 0.1. So n over n naught is 0.1, and you can then use E equals minus lambda t into this equation. But first, you need to work out from the half-life that they've given you, you've got to use this equation, which is a very common question in this exam. You've got to use the natural log of 2 to convert the half-life in seconds to the decay constant, which is kind of the probability of decay, into its inverse of the half-life with the conversion factor of natural log of 2 on the top. Okay? And you can leave it in whichever units they give you. It doesn't have to be in seconds. Excuse me while I have a sip of coffee. Okay, so once you know what the decay constant is, you can put it into here in this equation, which I've done. And the time is what we want to work out. So to get rid of the E, you take natural logs. Then the natural log on the left-hand side is the natural log of 0.1. And on the right-hand side, it basically gets rid of the E value, and the constant, the lambda t comes out of the power. Yes. All right, so this is the most difficult maths you need to do in year 13. For those of you who are just doing AS maths, it's not a problem as long as you remember how to take natural logs, because this is also what you had to do when you were talking about the decay of current, for example, in a capacitor. It's the same mathematics. So now you change the subject to the equation, and you notice the natural log of 0.1 is also negative when you do it in your calculator, so it will cancel out this negative here and let your calculator do the work for you, and you'll see the answer comes in years to 2.51 times 10 to the 5 years. I've chosen 3 significant figures, yes, because here they've given us the half-life to 3 significant figures. So I think time should be to 3 significant figures, but then you can round it up to approximately 2.5 times 10 to the 5 years as 2 significant figures. That's the time taken for 90% to decay approximately. Okay? So that's your 8 marks for radioactivity. And once you've done one question like this, you'll see that the grade boundaries are very high in Unit 5 because everyone is able to do it if they have done the hard work and learnt their equations and has recognized that it's a repeat of the questions. So Unit 5 is very mathematical, and therefore if you're good at maths and you've done your revision, you should be able to get quite high marks in Unit 5. Remember, there's 3 stages of learning physics. The concept, that you've got to understand why it's happening. How does it happen? How does physics work? That's just the ideas in physics. So half-life, for example. Then you've got to know the maths, and then you've got to problem solve. So you've got to be able to read the question and understand what they're asking. Okay? And the only way you can do the final part is by practicing as many past papers as you can, which is why I recommend that students who are doing linear use the abundant modular exams as their practice. Okay, so practice in modular and then do your exam technique, timing, mock exams, use the linear because there's only 1 per year. Here's question 17. In France, scientists from many countries are working together to build the International Thermonuclear Experimental Reactor. Okay, so it'll be fusion. Okay, so on their website it's written, fusion is the energy source of the sun and the stars. In the core of these stellar objects or stellar bodies, hydrogen nuclei fuse into helium nuclei and release tremendous amounts of energy. Where does that come from? E equals mc squared. So when you're fusing, you also get a mass defect. Okay, explain why there is energy released when hydrogen nuclei fuse to form helium nuclei. Okay, so Well, I always say to my students when they're learning it in GCSE, why do penguins huddle? They save energy by being in a group. And it's the same if you have nucleons, which are protons and neutrons. If you put them together in a more efficient nucleus, the mass decreases because they're saving energy, and they can release some of their mass energy back into electromagnetic energy. Okay, so in the fusion process, you're creating something more energy efficient, yes, which we say the binding energy is increased. So it's a good analogy. The reason penguins huddle is to keep the heat inside rather than losing it. Okay, so the same. If nucleons are together in a group, there's a more efficient structure formed. So mass decreases in the fusion process, and this decrease in mass is converted into other forms of energy. Yeah, according to Einstein's E = mass defect times c squared. So mass energy is what's conserved, yeah? And a bit like in chemistry, like you have exothermic reactions, if you have mass decreasing, it's like you've got an exothermic nuclear reaction. So it's not quite, we don't use the term exothermic, but it helps you get the concept. So remember what I just said? To understand physics, first you've got to understand the physics. So the alternative is to write the binding energy per nucleon in helium is greater than in hydrogen. In other words, helium is more stable than hydrogen because it's kind of saves energy with the group mentality that I explained to you. Okay, well, mentality may not be the right word, but I think you get the concepts. The concepts are number one in physics, and then so you haven't done any maths, we just explained the concept. Okay, now you would be able to do the maths, yeah, because you've got to just put numbers into that equation. So maths is not the problem. Yeah, it's problem solving, which is a problem. That means understanding what the question's asking. So part B, it says, it is hoped that this reactor, ITER, will be the first fusion device on Earth to maintain nuclear fusion for long periods of time. So why is nuclear fusion a problem on Earth? Is because it happens in stars because it has very high temperature. It needs very high temperatures. And we're talking about millions of degrees centigrade. So obviously, if you're talking about high temperatures, you've got to contain the matter at that temperature. In a star, the matter is contained gravitationally, so it doesn't have any container as such. To achieve fusion, the reactor is a hot plasma is used. Okay, so hot means very high temperatures. Okay, so the plasma must be at an extremely high temperature, and therefore also have sufficient density for fusion. Because if there's a high temperature just means a high mean kinetic energy of the particles. Yes? High temperature means high mean kinetic energy. But if you don't have enough particles in there, they're seldom going to collide. You want them colliding. If they don't collide sufficiently, then you're not going to get the fusion reactions occurring. Okay? So you need high density and high temperature. And then it says, explain why each of these two conditions must be met. Okay, so now this is verbalization. So this is a kind of problem solving, but instead of it being mathematical, it's conceptual. So you've got to be able to communicate clearly. Excuse me. You have to be able to communicate clearly your conceptual understanding. So, first of all, high temperatures. High temperatures means the high kinetic energy of nuclei. Okay, 1 mark. To achieve fusion, comma, should be a comma there, nuclei must get very close. And by very close, we're talking about nuclear sizes, so 10 to the minus 15. Remember, 10 to the minus 15 meters is the size of a nucleus approximately, whereas an atom is 10 to the minus 10 meters. So nuclei must overcome the repulsive electrostatic forces that exist between them, like protons, both positive, as they are all positively charged. Yeah? High kinetic energy is essential for this to occur. So if you've got enough kinetic energy, even though there's a repulsion force as you're approaching another positively charged object, it will not have enough force to slow down and work against your kinetic energy sufficiently to slow you down to a standstill. if there's a high enough temperature. That's why we're talking about millions of degrees centigrade. If enough nuclei collide per unit time, yes, per second, then the high temperatures can be sustained. If they don't, the temperature will drop. Yeah, and you need to sustain a high temperature as it's essential for fusion reactions. Okay, so it's like a circular argument. If you create fusion, you create more heat, more energy, and more energy creates more kinetic energy in the particles, and more kinetic energy maintains a high temperature, because temperature and kinetic energy of particles is the same. So remember this topic, nuclear fusion and stars, is really based on thermodynamics. So this is linked to the thermodynamics question. So you can't separate topics 100% into neat units. So think about what we learned in the kinetic theory of gases. So it's why thermodynamics and astrophysics are in the same unit of work. If the density is high, the collision rate will be higher. The higher the density, the higher the collision rate. Therefore, the more probability of nuclear fusion. Okay? So that increases the chance of nuclear fusion. So I think I've got 5 arrows there for the 4 marks, and we can have a look at the mark scheme and see how well I have verbalized it. So there's 16A. Yeah, mass defect. And there's the radioactivity question. Working out the time taken. So when you're doing this, look up what ln's 0.1 is on your calculator. You'll see it's a minus number. And part C. Oh, did we not have a part C then? Oh, it's question 17, isn't it? Okay, it's not the continuation. In the fusion process, energy is released, and then here's alternative ways of getting the second marking point. Okay, these are the concepts that you need to be familiar with. So you need to learn this kind of language. And then 17B is what we just did. Yeah, high temperatures, high kinetic energy, nuclei must overcome repulsion, blah, blah, blah. So the nuclei must come to fuse close enough to be able to fuse, and we're talking about approximately 10 to the minus 15 meters. 10 to the power of minus 15 meters, sorry about my scribble. There was one person who actually asked me what I use in terms of my annotation. I'm just using an Apple Pencil, and I like low tech because basically I do the PDF, I write my answers for my students in class, I bring them home, and when I got a chance I verbalize what I have explained to my students in class already, and if I haven't had time to do that, then I tell them that the rest can be found on YouTube. Okay, so I'm just using an Apple Pencil. Sufficient density so the collision rate remains high, and sufficient collision rates maintains a high temperature. So those are the 4 marks, and they're giving you 5 ways of getting the 4 marks. Okay, and now we're going to go into binding energy per nucleon in part C. Yeah, so they're going to give us a binding energy per nucleon graph. We're going to calculate binding energies. Yeah, again, energy is going to be released, and the energy released is due to the going up the curve towards the more stable elements. Okay, so it looks like we're talking about hydrogen, tritium, and helium, and this time they're giving you your units are mega electron volts. So they expect you to know how to use mega electron volts, any kind of electron volts, all the gigas prefixes you need to be familiar with from year 12 and before. Okay. And joules, of course. So you need to know how to convert them. So part C, they're giving you the binding energy per nucleon graph. Yeah, binding energy means how much energy is holding the nucleus together. And then by dividing by the number of nucleons in a particular nucleus, it's a fair way of comparing which nucleus is more stable. And basically, the higher up you go on this axis, the more stable it becomes. So more stable are high, and you can see hydrogen is lower on the stability because they aren't saving energy when they are not in a group. Okay, so the graph shows the variation of binding energy per nucleon as the proton number increases. So here we got the proton number. Okay, so bigger nuclei here. As the nuclei's charge size increases, you can see the binding energy increases and then kind of flattens out. Yeah, doesn't continue to increase at the same rate. In fact, sometimes it can decrease. So there is a perfect shaped nucleus, which is iron. Okay, element number 26. In one possible fusion reaction, a nucleus of heavy hydrogen, hydrogen 2, fuses with another isotope of hydrogen, hydrogen 3. So deuterium and tritium collide, hydrogen 2 and hydrogen 3, and you can see the numbers balance if they then can produce a helium nucleus and then free up a neutron. So it's a balanced nuclear equation, and the nucleus of helium and a free electron are produced. Now they want to know, is this energy efficient? Determine the energy in mega electron volts released. So they're assuming it is going to release energy, and in a minute we'll see why. You'll see we got hydrogen 2 is 1.1 mega electron volt of binding energy per nucleon, and hydrogen 3 hasn't, oh there it is, hydrogen 3 is 2.8 mega electron volts per nucleon. Now you can see helium 3 is not very high up on the binding energy curve. Excuse me while I take a sip. Okay, and you'll see that helium, I'm going to put it in green, has a very high binding energy per nucleon, about 7 compared to the hydrogens and helium-3, which are below 3. So we're making something more stable as we go from there to there. So going up this curve, going up this graph, increases stability and releases mass energy. Okay? So we want to work it out in the energy released in mega electron volts when the fusion happens. Okay? So we've got to use the values from the graph which I just circled for you above. The binding energy for hydrogen I read off as 1.1 from the graph. For tritium, hydrogen 3, 2.8. So this is what we started with on the left-hand side. That's kind of like the mass energy, but we don't have to put it into units. We can just do it in mega electron volts and compare the mega electron volts, because remember, energy and mass are equivalent. They're proportional to each other. So and the helium goes up to 7.0 when you form it after. Now we're not counting the nitrogen, because the nitrogen on its own has no mass defect, because mass defect or binding energy is how much it would change if you separated it into its individual nucleons. And of course a nitrogen on its own has no binding energy, okay? Because it's already separated. So the energy released will be the binding energy after minus the total binding energy before. Now remember, binding energy and binding energy per nucleon are mathematically different. So you've got 4 nucleons at 7.0 in the height. Yeah, so all these 4 nucleons are now at 7. They're level 7 in the graph. And before, 2 of them were at 1.1. Yeah? And 3 of them were at 2.8. So we had 5 nucleons, and then we had 4. And because the nitrogen is, the neutron has gone out. So you've got to multiply by the number of nucleons at each level. And that's how you get the change in the energy released, 17.4 mega electron volts. Hope that makes sense to you? Yeah? So because binding energy, you've got to note, binding energy is the energy holding the nucleus together, yeah? Or the energy required to separate it back into its constituents, neutrons and protons, okay? And therefore the binding energy is equal to the binding energy per nucleon multiplied by the number of nucleons. Okay? So remember, the binding energy per nucleon is a way of comparing the stability of different nuclei, whereas a large nucleus will have more binding energy than a small nucleus because it's got more nucleons at that energy level. Okay? So I hope you found that useful. This is 9 marks, and I have now completed the video on all of the nuclear and radioactivity-based questions. Okay, so thanks for watching. Yeah, I'll put them in the same playlist, and you'll now see that part 3 is ready for watching. Parts 1 and 2, if you haven't watched them already, go back and watch them if you want to. And don't forget to show your appreciation by liking every video you watch. There's so many people who watch them and don't show their appreciation or gratitude. And I was like that when I used to watch YouTube videos before. I just thought, well, someone's made it, so what? I'll watch it. And I still do that. But if you want more videos like this, and it's for your exam preparation, the more likes and shares I get, the more videos of that nature I will make. For example, I haven't made as many linear because most of my students are doing modular on YouTube. But I'm starting to make linear videos as well. So if you want more linear videos, you need to make sure you share them with your friends so we have more linear students watching my videos. Otherwise, I'll continue to focus on the videos that get the most likes and shares. Okay, and don't forget to subscribe. Thanks for watching. Bye for now.